Hello everybody and welcome to our webinar. Today we want to talk about our new release of MSC Apex Generative Design in the version 2020 Feature Pack 1. My name is Thomas Ryer and with me is Anne Duchting-Roch. So we want to talk today about the new functionalities, about what you can do with MSC Apex Generative Design. But of course, first we want to have a look at the idea behind, about what do we think generative design is made for, what is its purpose, and why do we think that this is a solution that you should use. At first, let's have a look at this bracket. This is an aerospace bracket and was designed by our software with nearly no manual effort. So we have gained a huge weight reduction while reducing the fixation points, so the amount of assembly, etc. afterwards, and getting an assembly into one integrated part design. All of this with just a few minutes, so around about 10 to 20 minutes manual effort and 2.5 hours calculation time. And now it's ready to print. So the idea is that an engineer can put in whatever he wants a design to be like, as well as the occurring loads and the surrounding system, and then the software is doing everything for him. He can change the direction of the system, but the system will do the work for him. This comes to something where I want to cite Ralf Sundermeier, the head of CAE methods at Volkswagen. He said that in 2025 virtual computation is used at every engineer's workstation. And this is needed for that. CAE processes must be operable without special expertise. This is exactly what we are working on. We want our customers to work with highly complex systems in the background, but with a very easy usage, without the need of a lot of training, and use it every day. This is needed because there is an expected transformation of the market within the next 20 years, where we do see a big shift from the conventional manufacturing technologies like stamping, casting, molding in the real world to something in the digital world. So we expect that the market will shift to digital twins to work in the digital world more and more, and all of this now covered by 3D printing, what is exactly in the middle between the real and the digital world, because it combines both worlds by having just digital information and making real parts out of it. And one very important point of this is generative design, because generative design works fully in the digital world, but it takes care of what happens in the real world, and thus is boosting 3D printing, and both together gets really a benefit for the customer. So when we talk about generative design, often people say, well, we know topology optimization, this is 20 years old, why do you talk about that nowadays? Well, topology optimization might be a tool behind generative design, but generative design is much more, because if you have a look at standard topology optimization tools, then you get results like in these 4 pictures above, where you are not sure about the design and you have to do a lot of manual work. Like in the existing topology optimization workflow below, you see that there are a lot of manual work icons, because you have to take care of mesh generation, about the finite element method setup, etc., etc. And in the end, after you get an optimization result, you still have to rework this result with a lot of manual effort and high complex CAD systems. And we don't want that. We want the customer to easily use the high complex systems behind, so that we can get to the goal of using CAE processes at every engineer's workstation. Why do we want it? We want to get this digital transformation, and we want to get designs that are as good as nature. Nature is really a good engineer. Like this tree It only uses material where it's needed. Nature is very sure to not use too much resources, and it's perfectly adapted to its surroundings, to the load cases, to the wind forces, or whatever. But it is a lot of work. It is not that easy to be as clever as nature. So personally, I don't think that I am clever as nature. So I'll take the right tool for it. And there we do have two hurdles. We have to have the right tools, and we have to have the right manufacturing technologies. So this is where we come to the fit of 3D printing and generative design. Because 3D printing is capable of producing these high complex organic looking shapes. But the design is still a topic. The topology optimization, well, it's just made for experts. It has a lot of manual work. It takes a lot of time. It's very costly. And in the end, if you redesign it by hand in a CAD system, well, you will not manage this high complexity. So we talk now about rethink the existing. We think that you should concentrate on the design for additive manufacturing core. So really talk about what do you want to have and what do you want to manufacture, and not how do I get it into the system. So we want the customer to have a very easy usage and to get the complexity hidden from him. So for example, the boarding pass below. All of us know standard boarding pass for an aircraft. It is very confusing, and if you're rushing through the airport, you will not understand what is everything there, and you search your information. Well, why couldn't a boarding pass look like the right one, a lean boarding pass, where you do have the same information as on the current boarding passes, but it is made for the user, it is made for the customer, and he can easily see his information that he is needing. And beside that, there is still a barcode on it so that the machine still can get the information. And we have thought the same for generative design. It is based on finite elements. It is based on topology optimization. But the customer does not have to care about it. He can set up his model by setting up the boundary conditions like loading and fixation areas and his goals. And these goals are not necessarily be mathematical goals. It can be something like I want to have a high complexity. So what is complexity? How is it measured? I don't know, but I don't care about. I just put in 2 or 3 values, have a look at it, and then decide which one fits to what I believe is the right design for a part. So I believe it is the right design because I know that the software takes care of that all the mechanical functionalities are fulfilled and that all the loading conditions will survive. And in the end, the system as well takes care to put this back into a CAD file, to use it anywhere else, and to run a verification on it. So everything automated, and I really just need to say what I want, and the rest is done by the software. To get this high automation degree is important because we think that variety is a key for successful designs. You have never a straight path to success. You always have to try different things. And this is what an engineer today is doing during designing a part. He's thinking about different designs, he's trying it out, and he recalculates it, and in the end he has done a lot of work for nothing. Okay, well, not for nothing, because he has found the best possible design. And we say that this can be done by the software. So as you look here, we do see a lot of different designs. All of these designs are fitting to the needs, are fitting to the boundary conditions. All of them will carry the load and fulfill its task. But they look very different. Some of them will be easily manufacturable, some will be very lightweight, and some will be easy to clean. And this is why we say we generate a lot of fully feasible designs that can be used, but then we put them into a design funnel where we say, okay, I want to have a very lightweight, but not the last grams out of it. because I want a design that fits my aesthetical needs. I want to have a part that looks nice. Well, I'm okay that I will not have the most lightweightest one, but the second most lightweightest one, but something that looks good as well, or that is good cleanable. And in the end, I'm deciding on a part that is good to manufacture. So taking care of verifying the part design for manufacturing, like with Simufact additive or with Digimet AM. So we say we increase the efficiency of an engineer because he has less effort for setting up the designs and generating designs, but has a high speed of generating these. So he can do multiple design iterations with changing the parameters to really what he wants to get in one day, so that in the end he gets better designs in a shorter time. And this comes overall to a cost reduction. Because we have a high degree of automation, we can run through a lot of different parts, or maybe the same part but with different loading conditions, because we do not yet know how the overall system will work, but we can automate that. We can go for lightweighting. Lightweighting always saves costs as long as we do not have to pay extra for saving weight. Well, we do not have to pay for the extra engineering amount, and we do not have to pay for saving weight when we are talking about 3D printing, because less printing is less expensive. And all of this was a big time reduction, because we can get a pretty much shorter time to market and in the end save a lot of costs. So we say that we can get from data to creativity with intelligent software. So all of this, we say it's intelligent. Well, it's just algorithms behind, but we say that if we have a look at this wheel carrier, you can see that the attachment points as our data. We do have information on these, which is the loads, and we gain knowledge about how they are connected by finite element calculations. And if we put all of this together and get some additional parameters inside, then we are gaining creativity. And creativity that fits all the needs is something like intelligence. So this is what our software does. And if you put all of this now onto your part, you can design for sustainability. You can reduce weight, you can reduce material during production and of course during usage. You can reduce the production time, what saves money, energy and everything. And in the end, you can reduce energy during production. Less material is less energy. And during usage, especially for aerospace or space, but as well for machinery. So if we talk about this, then we talk about where should I use it? Of course, whenever we are talking about 3D printing, it's made for it, it fits perfectly together. I said this in the beginning. When we are talking about lightweighting, and when we're talking about time efficiency and time to market, you're just faster with the software. And then you can use this in industries like 3D printing, space aerospace, this is nothing new, but as well for automation systems like robotics, gripper, packaging machines. All of these benefit of lightweighting designs and of getting better designs faster. So in the end, designers and DFAM users will take care of this software. They will benefit of it because they can now use CAE systems at their workstation without special expertise. This is where we have started. So you can overcome aged design thinking, lengthy design processes, and missing expertise for 3D printing. Our designs mostly are very easy to print. So this is a big benefit. And if you think, well, you might do an optimized part design over here, but it's a lengthy process. No, it isn't. Just try out. Like the bracket in the very beginning, it's 10 to 20 minutes setup time. Just try it if you gain a big weight reduction or whatever, a big benefit out of an optimization. And if you do, just let it run through to the end and you're done. So you can very easily get very lightweight designs. So now let's have a look at what is really possible with the software. What is the outcome? The first one is the wheel carrier for Formula Student racing team. It is made to connect the suspension system with the wheel hub and to assemble as well with the braking system. So the part is burdened with a lot of different loads like acceleration, deceleration, cornering, etc. And it is needed to be very lightweight. So we have gone through this optimization and gained around 50% weight reduction to what was there before, with around 80% time reduction for the design time. So beforehand, this took weeks, and now this can be done in hours. And all of this with a very equal stress distribution. Of course, a good stress distribution is key to save weight, but as well, a good process. A highly automated process with a software that is directly preparing the files ready for printing. This saves time and gives more time to have a deeper look at what is really happening in the part, to understand the load paths, understand what can be achieved with changing which values, and by that get a better design faster. And with a better design, the car gets faster. Another one is a satellite bracket that was made together with Trumpf and Tesat. So Tesat is building these parts, and they were asking us to get to a more lightweight design that can be easily 3D printed on a Trumpf machine. So we have went through the already known process and gained a 55% weight reduction to the already very lightweight design that is sent to space. So we can assume that the designers for satellites know what is lightweight design, but we have gotten even 50% weight reduction on that. And this with 30% stress reduction inside the part and 80% stiffness increase. The stiffness increase is highly important, especially for the launch of the rocket, because there very high vibrations occur, and these can destroy parts that are not stiff enough. So as well, we have printed this part on a Trumpf machine, and it was very easy to be printed because, as I already said, the parts that are coming out of our software are mainly very easy to produce. And in this case, it was very easy to print. And the last one I want to show to you is this light hinge. And this one was made by EDAC. EDAC had already done an optimization on this part around 1.5 years or 2 years ago already. And now they have gone through the process with our software again, and they have gained 70% weight reduction to the original part. 70% is quite a big number, but what we are very proud of, and even more proud of than the 70%, is additional 40% more lightweight than the conventional optimization. So they have done an optimization with some already known optimization tools, and with our tool, they are 40% more lightweight than with the other optimization, and with 60% less time effort. So they are really impressed on how good the results are in how short time. So it's really fast and really good. So this is all from my side. I now hand over to Anne, and she gets into the technical side.
So let's get technical. I would like to start with a first glance at the workflow of MSC Apex Generative Design. We are starting with the geometry preparation. This can be done directly in MSC Apex Generative Design, or an already created CAD file can be imported. Followed by this comes the geometry and boundary conditions preparation. So we are defining our boundary conditions and afterwards set them up in events and add the optimization parameters. This is everything for the model generation, and we can directly start the optimization. The program automatically transfers to the post-processing, where we can have a live view of the optimization and see our structure evolving. You might also notice that with the FP1 release, we have added an automatic intersection, and you can see your finished design in the post-processing. Also, with the new functionality Mesh to Cut, we can directly transfer our optimization result back into a cut file and use MSC Apex structures for reanalysis. So let's have a look at the software. I'm presenting to you our bookshelf tutorial, which is a very simple and easy part and a very nice setup. We are starting with importing the geometry I've already prepared. You can also find a tutorial for this on our help website. After importing the geometry, we will start by setting up our material. In this case, I'm using a regular steel. I'm inputting the Young's modulus and the Poisson ratio for the optimization and the mass, so for the mass, the density, to have a visualization of this in the post-processing. You can see that I can easily manipulate the units here and the calculation is done automatically. Now I'm assigning the material to the solid and we have our first definition ready. Next up, we will create the non-design spaces, so the spaces on which the boundary conditions are applied. Therefore, I'm using the offset method. I'm choosing 3 sleeves for the screws to fixate the bookshelf to the wall. And then I'm going to choose the top plate to apply the force for the books. You can see that all of our created non-design regions are visible in the model tree. So let's create the force. As I already mentioned, we're just putting one force as a representative for the weight of the books on the top plate. We are choosing the cell option to apply the load, and we are applying 3 fixations to the 3 sleeves we've already created. After this is done, we are finished with our model setup and you can have a look at this in the model tree. The next steps are done in the Studies tab. We can see our design part in here, and we can also see that the optimization setup is not yet finished. We can create more events and apply our boundary conditions to these events. For this case, we will just have one event. Next, we are defining our stress goal, in this case 2 megapascals. And everything else stays as it is for this first optimization. Of course, you can always change the import, the parameter strut density and shape quality to achieve different results. Also, you can add the GPU option in the advanced user settings and then go ahead with the optimization. You can see that we are transferred automatically to the post-processing while the simulation is already starting in the background. So you can have a live view now of the optimization and see how your structure is evolving and how the material is reduced, your stresses are changing, and your structure with it. We will now skip this part and go directly to have a look at the result files. Here we can see a video of the already prepared optimization, which is running through very smoothly, and the result geometry gets finer by every iteration and more defined. We can also have a view of the design space and see where our optimization is reaching the design space limits and where the material was left out. We can also have a look at our displacements and the design mass. For the comparison of different strut densities, I'm now showing you the different models. This is the strut density medium, and if we go now to the strut density dense. In here you can see that the design has changed a lot. We have a lot of more struts and also a lot more shell structures. This design is probably a lot heavier than the other one, but for some cases, for example heat transfer, this could be a design we want. So with the strut density, you really influence the design of your part. Next up, we have the strut density sparse. You can see that there are only a few struts created and they are more massive than the ones before. So we have a design that's really just a few struts and is, for example, more easily to clean. So it really depends on your other boundary conditions and maybe other conditions you cannot put into the optimization to see which result you want to have. Afterwards, you can export your design candidate and get it to the printer. So let's find out more about the new features. Now we will have a look at a very simple bracket. Therefore, I'm importing the design space as I've done previously for the bookshelf example. First of all, we are creating the material. In this case, it's again a regular steel with the Young's modulus and the Poisson ratio. The density is just for the mass calculation in the post-processing to have a good overview over the design that comes out of the optimization. We will now assign the material to the design part. As you can see, the material as well as the assignment to the part is listed in your model tree. Next up, we will start with the non-design region creation. In this case, the non-designs are already available as separate cells and we can directly select them as such. We can see all our non-design spaces are created and sorted to the non-design regions, and we can show our design space again. Now we are creating a local coordinate system for some of the forces we need. We are inputting our values and we are defining the surface where we want to apply it to. Next, we are defining our loads. In this case, we are using the remote force application method that's new to the Feature Pack 1 release. We are inputting our values as usual, and we are selecting our cells we want the force to be applied on. In this case, I'm selecting 2 cells and then select the point in the middle of these cells as the point of application. This can be done either by selecting the point already suggested from Apex, or you can just click somewhere else and you can input your coordinates you want your force to be applied on. This is very nice if you, for example, have a mass you want to be considered in the optimization and you just put the force or the gravity load of this mass on this point of application. Next, we are using the external orientation method to apply another load on the non-design spaces, but in this case in regard to the earlier created coordinate system. One thing is left to do, that's the definition of the displacement constraints. In this case, we are selecting all of the other not already defined non-design spaces to create one constraint. This is very important for some of the functions I will show you just in a few seconds. The optimization parameters are defined in the Studies tab. We are defining a second load case, so a second event for this optimization, and apply the forces accordingly. We could also change the strut density and experience some different outcomes, but for the first optimization, we'll leave it at medium. What we are changing is the complexity. We are inputting a lower value, and we can just see in a few minutes, in a few seconds, how this turns out. we are setting up the stress goal, and we are deciding that not all non-design spaces that are marked as constraints need to stay in the result. Now the optimization setup is ready and finished, and we can start the optimization. We are automatically transferred into the post-processing and have a look at the evolving structure and of the progress of the optimization. We can see that very fast the first material is reduced and the structure is evolving. The result is a very clear structure, and you might notice that the complexity is not that high, so we have just more or less the clear stress and load paths we can follow. Of course, we can have a look at the design space, and you might also notice that we are missing some of the fixation points. But this is something the software is capable of doing. So while choosing or while deactivating some of the keep non-design spaces, we are allowing the software to reduce the number of fixation points. This is very good and important if you want to do a part consolidation, or if you want to reduce your fixation points but don't know which ones you can reduce. You can just let the software decide which ones are needed for your loads and boundary conditions and have a look at the designs afterwards. Next up, we are having a look at the complexity setting. So how does the complexity setting influence our design? We are comparing a complexity of 6 and a complexity of 20, and you can see in the results that a lot has changed. The structure has evolved. Of course, the main force paths are the same, but there are more details in the structure. That's because we have increased the resolution with the complexity. Followed by this, we are comparing what the keep non-design function is really doing and how it influences the design. In the first example, we have seen that the non-design spaces are allowed to be reduced. In the second optimization, we now say the software is not allowed to reduce any of the fixation points and needs them all in the structure. As you can see in the result, we have a very different structure. We have one that includes all of the non-design spaces and one that has a few left. You might also notice that the one with the fewer fixation points is probably more lightweight than the one which includes all of your fixation points. So if you really want the lightweightest design, you want to use this function to reduce your fixation points. For the last comparison, we are having a look at the stress goal. We can set up different stress goals for different events and thus prioritize them differently. This way we can include overload cases and take into consideration the different meaning of the different events. You can see the changed structure in this example. So, what are the new features of the Feature Pack 1 release? We have the automatic intersection, which takes place after every optimization iteration. We have the scenario-specific complexity setting, so we can set up different complexity settings very easily and compare them in the post-processing. We have the reduction of fixation points versus the keeping all of the non-design regions. So we can see that we can really reduce parts if we want to, but if it's not allowed, we can also tell the optimization algorithm to keep all of the non-design spaces. We have the event-specific stress goal, so we can prioritize events differently. This is very useful for overload cases. And we have another feature I would like to introduce to you now. It's the command line optimization option. So Now you have the option to not just only start your optimization directly in MSC Apex Generative Design, but export your already created model setup and run it in the background. For this, we are having a look at the bookshelf tutorial again and at the already prepared model, and we are just going to export it. The software automatically creates a folder for this model and inputs all the necessary files for the optimization. For example, the configuration file. In here are all the important definitions the software and algorithm needs to fulfill and to carry out the optimization. Also in the folder are the STL files that are the input files for the geometry. We now have to start a PowerShell in the optimization folder and enter the path to our program. After entering the path, we can just hit enter and the optimization is carried out. You can see that we are now seeing all the output the algorithm gives, and on your right hand side a folder has been created where the results are being saved in. Of course, the GPU option is also available with this function. After creating the output, we can also import these optimization results back into MSC Apex Generative Design. For this, you will have to choose the optimization folder and input the original design part. This way, you can have a look and compare your design part to the generative design result. This just takes a few moments, and now all of your results are imported into the program. You can have a look at these in the post-processing. Of course, you can view the run-through of the optimization and have a look at your stresses and displacements. So the last feature I would like to present to you is the new Mesh to Cut functionality. Therefore, we are using this already calculated model and go back to the modeling. We are importing the optimization result, the main data STL, and you can see it is imported into your model tree. To use the Mesh to Cut functionality, we are going to the Geometry Edit tools and selecting the Facet Body to NURBS geometry option. In here you have the choice to use either the automatic size calculation for your mesh, or you can input your own face size. For this model, I'm just going to select the automatic size calculation and I'm starting the meshing. After the meshing is done, I can click Facet Body to NURBS so I can verify that I really want to use this calculated mesh, and the NURBS transitioning is automatically started. Once the NURBS are created, we get the status message NURBS is created based on partitioned facet body. So in this case, the transition to NURBS went very smoothly and the geometry is one solid. To finish this presentation, I would like to show you a performance comparison. We used this jet engine bracket on the right side with 4 events and calculated the optimization on different machines and different setups. We used some CPU calculations, which took about 209 minutes. And then we also set up different other optimizations with CPU and GPU calculation, which you can see evolved a lot regarding the time. So we went from 209 minutes to the first GPU, which took only 88 minutes, and up to a computer with 3 GPUs, which only took 14 minutes to calculate this model. Furthermore, we have some white papers and case studies prepared for you. You can also find out more information and get tutorials on our help website and contact our support.